Introduction to Water-Soluble Polymers. Section 4, Solubility and Sorption. We're now reaching the pinnacle of this polymer material. Since this whole course is focused on how polymers behave in solution, and in particular aqueous solution, this section is very important to your understanding of colloidal behavior, and in particular how to control that behavior. To begin this section, let's discuss the solubility of polymers. First off, we have the same old adage you were taught in your first chemistry class: like dissolves like. Just as with small molecules, nonpolar solvents dissolve nonpolar polymers, and polar solvents, in particular aqueous solutions, dissolve polar polymers. If the polymer is charged, even better for water. However, unlike small molecules, polar solubility can be affected by a few other things. Namely, I want to point out that as molecular weight gets larger, the solubility limit decreases. Temperature, however, does not have a consistent effect on the solubility for polymers. Raising the temperature helps some polymers dissolve, in others it hinders the solubility. Since cross-linking essentially makes one massive molecule out of the sample, or at least drastically increases the molecular weight, it makes a polymer insoluble. This doesn't mean that the polymer doesn't preferentially interact with the solvent, though. The polymer might not be able to dissolve due to the cross-links, but it can act like a sponge and soak up the solvent instead. The cross-linked polyacrylic acid layer of a baby diaper is a great example of this. It is used because it soaks up water but never dissolves. Crystallinity of a polymer ends up behaving like cross-linking, so it has the same effects on solubility. It significantly decreases it, if not eliminates solubility entirely. Please note that with all these scenarios, the dissolution rate is a major factor. In most cases, even when a polymer is soluble in a solvent, the time required to actually dissolve the sample is orders of magnitude higher than when dealing with small molecule solubility. I want to start by stressing a point which is oftentimes overlooked. When we are discussing solubility, we're really talking about the mixing of two phases, not just the movement of molecules into the solvent until there are no bulk phase molecules left. As shown here, yes, the polymer molecules move from the bulk polymer phase into the solvent, water for this course, but the water molecules are also trying to mix into the bulk polymer phase. This can be referred to as swelling. Now, let's look at the energetics and compare them with those we saw for the small molecules in the previous unit. We start with our familiar Gibbs equation and recognize that we need to overcome the enthalpy term with the entropy term to create a negative delta G, which in turn suggests that the dissolution of the polymer into the solvent will be spontaneous. So if we compare a polymer to a small molecule with the same functional groups, we see that the most significant change will be in the entropy term. Why? Take a look at this 10 by 10 grid, where I have 10 small molecules mixing in with 90 solvent molecules. I will let you do the permutations calculation on your own, but the number of possibilities for this is pretty high. The actual value is not what concerns me here. Now, compare this to the same grid here on the right, but a polymer made of 10 repeat units is placed in the solvent molecules instead. Because the 10 MERs are connected, they will always occupy adjacent grid squares. Hence, the number of possibilities in this scenario is going to be substantially less than the possibilities for the 10 small molecules on the left. Therefore, the entropy term for the polymer is much less than for the analogous small molecules. Because of this, the saturation concentration for the polymer is much less than its standalone MER or other small molecules with similar functional groups. From here, let's just go through some polymers to get some experience with a few more and to discuss their solubility. You've already learned some general solubility trends and rules for small molecules. Now let's apply what we know to some polymers. As we have been, we will continue on only concerning ourselves with solubility in water. My suggestion is that you use this section twice. On this first viewing, pause the video at the beginning of each slide and try to formulate your own opinion on the solubility of the polymers shown. Then play through it and learn if you were correct in your thinking or not. Your second viewing should be before you're tested on this material. Go through it again to see if you have retained the information and prove to yourself that you can pass this section on the exam. You ready? Alright, let's get started. One of the first things which I look at for water solubility of a polymer is the backbone. Just like with small molecules, polar atoms help solubility. In this case, cellulose, which has plenty of polar oxygens along the backbone, is soluble in water. I should note that although cellulose is documented as soluble in water, because it is most often found in the semi-crystalline state, it takes a very long time to actually dissolve it. On the other hand, something like polyethylene, which is all carbons and doesn't have any functional groups, is insoluble in water. However, just because the backbone is entirely composed of carbons doesn't necessarily mean that the polymer in question will not dissolve in water. Let's take a look at a few more examples to see why. Shown here are 3 vinyl polymers. You'll notice that they all have the same appearance with a single functional group coming off of a repeat unit with 2 carbons in the backbone. The only difference here are the actual functional groups. Now let's use our knowledge of small molecule water solubility. Take a look at polypropylene. It doesn't have any polar groups. It's a pure hydrocarbon made only from carbons and hydrogens. It is most certainly not going to be soluble in water. How about polystyrene? Do its functional groups add any polarity to the molecule? Nope. So it's not too surprising that it isn't soluble in water either. Polyvinyl alcohol, on the other hand, has a nice little polar OH group on every repeat unit. This ends up being enough to render it soluble in water. There are numerous acrylic-based polymers out there. Let's compare and contrast a few. The base model, polyacrylic acid, is commonly abbreviated as PAA. Using the information from the last slide, do you think PAA will be soluble in water? Its mer does have a lot of polarity with the carboxylic acid group hanging down. Due to this polarity, and even a little ionizing with a high enough pH, this polymer will definitely dissolve in water. Now let's look at polymethacrylate. There are numerous methacrylate monomers, all with an extra methyl group here. After polymerization, this methyl group is attached to the backbone. This decreases the flexibility of the polymer chain, and consequently decreases the entropy turn even more than acrylate-based mers. This should be a big clue to its solubility for you. I should mention that this polymer is polymethylmethacrylate because of the extra methyl group attached to what used to be a carboxylic acid group. Of course, now it has become an ester group. This polymer is abbreviated PMMA and is easily the most common of the methacrylate polymers. Due to its extra methyl groups, it is insoluble in water, as most methacrylates are. On the other hand, we can add more polar groups, as in the case of polymaleic acid. Here it is easy to see that additional polar groups will result in the polymer being soluble in water. Similar to the acrylates is the acrylamide set of polymers. Where acrylates had a carboxylic acid functional group, there is an amide group at every repeat unit for the polyacrylamides. Shown here is the simplest case, polyacrylamide. It is oftentimes abbreviated as PAM or P-A-M. Again, similar to the acrylics, the polarity of the functional group, the amide group in this case, yields it very soluble in water. If we look at a more complex version of the acrylamide repeat unit, methyl methacrylamide, as shown here, we are faced with the same dilemma as before. Will the added methyl groups counteract the polarity of the functional group? For the acrylate version, polymethyl methacrylate, it rendered the polymer insoluble in water. However, for the case of polymethyl methacrylamide, it remains soluble in water. Thus, I typically remember the trend that all polyacrylamides are water-soluble. Next on our list are the polyoxides. As shown here, these are polymers with not just carbon atoms along the backbone, but also oxygen atoms. Polymethyl oxide has a single carbon atom and a single oxygen atom along its backbone for each repeat unit. Polyethyl oxide has 2 carbons for every oxygen, and polypropylene oxide has 3, and so on. So the trend is to add more nonpolar groups. The first in this series, polymethyl oxide, is insoluble in water. The polarity of the single oxygen per repeat unit is not enough to counteract the nonpolar rest of the mer, which renders it insoluble in water. Now one would think that as more carbon atoms are added per repeat unit, and still only a single oxygen is left per mer, that the solubility in water would only get worse from here. Oddly, polyethylene oxide is soluble in water. It is often referred to by its acronym as PEO or PEG, which stands for polyethylene glycol, just another name for the same molecule. And then, polypropylene oxide reverses the trend and goes back to being insoluble in water. So what's going on here? The general trend is that polyoxides are insoluble in water, okay? However, the phenomena of polyethylene oxide's aqueous solubility is credited to its unique structure and therefore its spacing between oxygen atoms. The ethylene oxide repeat unit seems to fit quite nicely into the natural lattice structure of water. It is well known that adding ethylene oxide linkages, again sometimes referred to as ethylene glycol repeat units, will increase the aqueous solubility of small and large molecules alike. Therefore, PEO is the only polyoxide that is soluble in water. As a wrap-up to this quick guide through polymer aqueous solubility trends, let's look at some more unrelated examples and test ourselves. First on our list is polyvinylpyrrolidone, also known by its abbreviation as PVP. Notice the amide group? This combination of a double-bonded oxygen and a nitrogen to the same carbon was also seen in the polyacrylamide series. If you remember, those were all soluble in water. It should come as no surprise then that PVP is also soluble in water. Next, we have polybutadiene, or just PB. This is a fairly common synthetic polymer for rubbers. Notice the total lack of polar groups? Yeah, it's not going to be soluble in water. Along the same lines, polyisoprene also lacks polar groups. Not surprisingly, it too is insoluble in water. Lastly, polychloroprene, which is commonly known as neoprene, is shown here. It has a single polar group, the chlorine. However, let's not forget our everyday knowledge. Why does neoprene sound familiar? Oh yeah, because of neoprene rubber. It would be a little ridiculous to make a scuba suit out of neoprene if it was soluble in water, don't you think? So apparently, the 1 chlorine per repeat unit is not enough to dissolve it in water. Polychloroprene is definitely insoluble in water. Clearly, we have not exhausted the possibilities for synthetic polymers. Not to mention, we haven't even touched on the natural and semi-synthetic polymers. We are sticking to trends here, and the synthetic polymers offer us the most flexibility in making small changes to our repeat units so we can note how these changes affect solubility. In summary, when looking into the solubility of polymers, start with what you know about small molecule solubility. More polar atoms will improve water solubility. Charges always help aqueous solubility. This applies to both big and small molecules. For polymers specifically, some general trends include: acrylates are usually soluble. If there is no ester group, just acid groups. Acrylamides are almost always soluble, even when methylated. Oxides are insoluble, with the exception of polyethylene oxide, of course. However, if you are at all unsure, check out the Polymer Handbook to find out for certain. Don't just guess. After discussing the solubility of polymers, our next topic is how the dissolved polymers interact with surfaces. We will start with the typical non-ionic polymers. Just like when we discuss solubility, let's compare polymers with what we already know about small molecule adsorption. As with solubility, adsorption also takes longer for polymers than it does for small molecules. Also, because there is a distribution of molecular weights in the polymer sample, this means there will be a distribution of adsorption behaviors. Some other aspects of polymer adsorption we will go over are the effects of pores and the conformation of the polymer at the surface. To begin with, let's quickly go over some terminology. Shown here is an adsorbed polymer. We already know that the solid surface is referred to as the sorbent. We also see that not every part of the polymer is actually on the surface. The portions of the polymer which are still dangling out in the solution are referred to as loops and tails, depending on if they encompass an end of the polymer chain or not. The repeat units of the polymer that are in contact with the surface are referred to as trains. The ratio between how many repeat units are in trains versus how many are in the loops and tails is a function of molecular weight, time, concentration, and the interactions between the repeat units and both the surface and the solvent. To begin with, let's get the simplest case out of the way. When an anionic polymer is in solution and the sorbent is negatively charged, both have the same sign to their charge, that is, negative. As you can probably imagine, the electrostatic repulsion between the polymer and the surface won't allow for adsorption to occur readily. The same trend is noticed when dealing with cationic polymers and positively charged surfaces, but since the majority of surfaces have negative charges, if any charge is present, we will continue on with anionic sorbents. When there is coulombic attraction, as is the case with a cationic polymer in solution and an anionic surface, adsorption is significant. An isotherm will be helpful to explain the adsorption here. Typically, all of the dissolved polymer adsorbs to the surface until the surface is saturated, at which point the isotherm plateaus off. This is referred to as a high affinity isotherm, since the affinity of the polymer for the surface is so high. This is reflected in a steep slope originally, which is in turn quantified in a high Langmuir affinity constant, A. In comparison to an analogous small molecule adsorption isotherm, the cationic polymer's isotherm has a much sharper turn before surface saturation is reached. This plateau level is given the variable x here for simplicity's sake. There are a few other terms which help us quantify how the cationic polymer adsorbs. One such term is the charge ratio. It is defined as all of the charge from adsorbed polymer divided by the charge of the sorbent, which is oftentimes fiber. To calculate the charge ratio, you would take x, the adsorbed polymer at plateau level, multiply it by the charge density of the polymer, and divide it by the ion exchange capacity of the sorbent. This charge ratio doesn't explain the conformation of the polymer on the surface, though. Perhaps all of the polymer's charge is absorbed, or perhaps most of the polymer charge is left dangling in the solution, as the rightmost chain shows here. The adsorption stoichiometry, Q, is used to quantify the ratio of the adsorbed polymer's charges, which are actually in contact with the surface. For the example on the left, where all of the polymer charges are adsorbed, Q equals 100%. The polymer on the right would have a Q nearly equal to 0. Keep in mind that these two ratios are describing two different ideas. Q, the adsorption stoichiometry, is describing how much of the individual polymer is actually attached to the surface. On the other hand, the charge ratio is describing overall how much of the sorbent's charge is being offset by charge from the adsorbed polymer. The charge ratio can give an indication of how a polymer is penetrating into a porous structure. If most of the sorbent's charge is located inside pores, larger polymers will have restricted access to it. Thus, for porous sorbents, it is common to see the charge ratio for a given cationic polymer decrease as the molecular weight increases. Essentially, the large polymer coils can't find their way into the pores, so most of the sorbent's charge is unutilized.